Hello everyone, welcome to the course Network Theory. This is Dr. Satyavani Bandela, Assistant Professor, SR University, Warangal, Telangana. In today's lesson number 3, we are going to discuss Kirchhoff's current law. Before diving into this session, let us briefly discuss about previous topics. They are Introduction to Electrical Networks and DC Circuits, Basic Electrical Elements Classification, Ohm's Law and Electrical Power Energy Calculation. In lesson number 1, we discussed basic electrical elements, active elements, passive elements, classification. The next, what are the active elements? Example, voltage source and current sources are known as active elements, and RLC elements means resistor, inductor, capacitors are known as passive elements. And passive elements, their representation and units also we discussed. Let me draw passive elements. This is the resistor symbol and the R letter, and the unit of this resistance is ohm. And the next passive element, inductor symbol, and we are going to represent that inductor with capital L, and the unit is Henry. And the third passive element is a capacitor, the letter C, and the unit of capacitor is farad, and these three are passive elements. So passive elements and active elements. So what are the active elements? Active elements are either voltage source and current source. Okay, so these things we discussed, and even in classification of active elements, based on the magnitude of value, whether the voltage source depends on other parameter or not, based on the dependent source and independent sources, where the independent sources are represented with a circle like this, voltage source with minus plus or plus minus, okay, and the unit of this voltage source is V. If this is a current source, it is represented with an arrow mark, whether it is upwards or downwards. And here we will represent magnitude of current, whether it is 2 ampere or 5 ampere, like here it is 20 volt or 100 volt. Okay, so the magnitude of voltage or currents are given if that is independent source. If it is a dependent source, independent source, the symbol of a dependent source is rhombus, and there are 4 different types of dependent sources: voltage controlled voltage source, voltage controlled current source, and current controlled current source, current controlled voltage source. If this is voltage source, we are going to represent with plus minus symbol, and if the magnitude of this voltage source depends on other parameter, and here it is going to represented with some number and Ix, like this. It is not ampere, it is Ix. So the magnitude of this voltage source depends on other branch current. So like this, if I write here 2 Vx or Va, Vb, Va or Vb, or if that is multiplied with some number where this parameter is a voltage at particular branch in a network, means this is the voltage source, depends on magnitude of this voltage source depends on other branch voltage. Okay, so this is about dependent voltage source. If that is dependent current source, so first of all it is dependent current source. Current source means we have to represent current upwards or downwards. If this current source depends on other branch current, then you have to write some number. It need not be 2, some number into Ix. Like this they are going to represent in circuits. Ix is the current which are going to represent in a network through particular element. Now this is how we are going to represent current controlled current source. This is current source and controlled by other branch current. If current source controlled by other voltage, then we have to write some number, any number, that is 2, 3, 4, and it is multiplied by Vx, Vb, Vc, any. Means this Vx is the voltage in that network where it represents across that particular branch. Okay. So these four kinds of dependent sources we discussed, and active elements and passive elements also completed. In lesson number 2 we discussed Ohm's law. So what is Ohm's law? The basic Ohm's law is, provided at constant temperature and current through uh, conductor is directly proportional to voltage. So if I take one element, if this is the conductor and conductance of this resistance is R, if I apply voltage source across this element and current through this element I is directly proportional to applied voltage, and here the proportionality constant is 1 by R. Okay. So from this we can write V equals to, if I multiply, cross multiplication, so this is equals to proportionality constant, that's why. So finally V equals to I into R. So this is your final derived equation of Ohm's law. But what is Ohm's law states? Provided at constant temperature, current through this conductor is directly proportional to applied voltage. And here where R is the resistance of the material, conducting material. Okay. Then later after this Ohm's law we discussed power. So what is electrical power? Simply it is a product of voltage and current, that formula we have seen, and the unit is watt. Okay. The next energy. Energy is a product of power and time. So how much amount of power that is consumed by any device for how many hours. So that gives the energy consumed by the device, and we are going to take the product of power and time. So that may be in kilowatt hour. Generally we used to represent the unit of energy in kilowatts hour. So this is about the previous lecture 1 and 2. Now we will see today's lecture, that is Kirchhoff's current law. Kirchhoff's voltage law and Kirchhoff's current law, these are the two laws introduced by German physicist Mr. Robert Kirchhoff, and according to his principle, Kirchhoff's voltage law is based on the law of conservation of energy, and where Kirchhoff's current law is based on the law of conservation of charge. And according to his principle, the statements are given like this. Kirchhoff's voltage law states that algebraic sum of voltages in closed circuit equals to 0, and where Kirchhoff's current law states that algebraic sum of currents at node equals to 0. So now we will discuss what is closed circuit and what is the node. So node in the sense, in any circuit, circuit is already we have discussed electrical circuit and network elements in the first class. Now let me draw one example circuit. See here I am taking one circuit, electric circuit with one single voltage source and with a combination of 3 resistors. Let me draw 3 resistors, 2 resistors in parallel and one resistor in series. Let me take, this is R1, resistance 1, resistance 2 and 3, and the voltage source V. Now according to this principle, here we used a node, new term, node, N-O-D. Node is nothing but a point at which 2 or more branches connected together. So branch, again the new term. So what is mean by branch? See here in this network, from this point to this point, here it is a point where the 2 elements are connected together. Okay. So this is this element, this line is said to be branch, and here R1 is another branch, and this is R2 is one more branch, R3. So like we can divide this into 1, 2, 3, 4 branches are there, and here this is the point at which voltage and resistors are connected together. Okay. And here it is the point where three resistors are connected together. So, this is known as node, the point at which two here there are two elements or two branches connected together, and here three branches connected together. The point at which two or more branches connected together is known as node. Here we can say in this network, this is the node 1 and this is node 2. Okay. Now, according to Kirchhoff's current law, so it states that algebraic sum of current at node equals to 0, because the node where it is like a junction, it is also known as a junction. Okay. So, where at junction the current division takes place if at node two or more than two branches are connected together. That we will discuss in detail with an example circuit. So, this is about Kirchhoff's current law. Now, let us see by taking some currents in each and every branch with one example circuit. So, in this slide again it is given the statement of Kirchhoff's current law, algebraic sum of current at branch equals to 0, and the node definition, and see how the currents are taken. So, current entering, if the current is, just remember, if the current is entering to the node, if you are taking it as a positive current, if the current is leaving the node, you must take the current as negative one. Okay. So, you just remember this point. Algebraic sum means if the direction of current towards the node is taken as positive, then leaving the node must be taken as negative, vice versa. So, anything. So, like you have to consider the direction of current, based on that you have to identify whether we have to take plus addition of current or subtraction of current. So, like by adding all the current, algebraic sum of current at, it is applicable at node equals to 0, that we will see with the circuit diagram. See here in this picture, so this is the node at where 1, 2, 3, 4, 5. So, there are 5 branches are connected together, means in every branch there is a current and the current directions are also mentioned. See here, this is the branch 1 and the direction of current here it is towards node, and in this is branch 2 and this current is also towards node, and here this current is also towards node, and this current, fourth branch current, is leaving the node. If you observe this, leaving the node, and similarly the last branch, fifth branch current is also leaving the node. Okay, just now we are saying if the current you are taking entering the node, then if it is positive, then you have to take leaving the node current must be negative. Now we will see. See, entering the node, positive means I1 current is entering the node. So, plus I1 you have to write, and I2 current is entering the node, means plus I2, and I3 current is also entering towards the node. So, that is why it is plus I3, but where I4 and I5 are leaving the node, that is why minus I4 minus I5 equals to 0. So, this is how you have to apply KCL at node in circuit diagram. This is actually, this is not circuit diagram, to get idea about how to take the currents, whether it is positive or negative. We have taken one simple example. So, this now we will see with another circuit example. Let us take one example circuit with voltage source and resistors. Here our concentration is how to apply Kirchhoff's current law? I am taking one simple circuit with current numbers and see how to calculate unknown currents applying Kirchhoff's current law. Okay. Now here I am taking this branch current 7 ampere and here in this branch 5 ampere, but in this branch current I am writing X. Okay. So this is X. Now here it is, I am writing 1 ampere and let us take resistance. Let me draw this resistance here. So there is a resistor and in that resistance the magnitude of current, here I am writing unknown current Y. Okay. Then later here in this branch also unknown current Z. So now the question is find current magnitude X, Y and Z using Kirchhoff's current law. Okay. So before we apply Kirchhoff's current law, so first we have to identify the nodes because KCL. So what is KCL statement? Algebraic sum of current at node equals to 0. Is that right? At node equals to 0. Okay. So here how many nodes? Here number of nodes in this network. This is the node 1 because 3 branches are connected together. This is node 2, again 3 branches, and at node 3 1, 2, 3, again 3 branches. Okay. Now let me apply KCL. Here I am applying KCL at node 1. Okay. Now see, this current is towards node, 7 ampere current is towards node. Okay. If towards node, if plus 7, just now we discussed towards node, if the current is there positive. Okay. And where X current is leaving the node, this X current is leaving the node, that's why minus X, and at node 1 5 ampere current is also leaving the node, that's why it is minus 5 equals to 0. Then if I simplify this, I will get X equals to 2 ampere. So we got X value. Then next, how do you get Y current? Now let us take another color, red. Now here I am applying Kirchhoff's current law at node 2. Okay. Now observe the direction of current. At node 2, this X current is towards node. So towards node is plus. Is it right? At node 2 we are applying, that's why it is plus. Okay. This X is towards node 2. Now 1 ampere current is leaving the node. So what is the magnitude of this current? 1 ampere. Is it right? So if it is leaving the node, so what should I write? Y minus 1. And at node 2, even Y also leaving the node, this current is leaving node 2, that's why you have to write minus Y equals to 0. Okay. So we already got 2x value 2, here I am substituting 2x value 2 minus 1 equals to, if I write y right side, it becomes minus, y becomes plus 5. Then how much you will get? Y value 1 ampere. Okay. So Y value 1 ampere. Now see how do you get next Z current. Okay. Now where should I apply KCL? Now to get Z current. So now this is Z, it is connected at node 3. Now here I am applying Kirchhoff's current law at node 3. Okay. Then how many branches are connected together at node 3? 1, 2 and 3. And see the Y current towards node means plus Y. Okay. Then next, Z current is leaving the node, so it is minus Z. Okay. So, and here in this branch 5 ampere current is flowing like this. Is it right? So, this is 5 ampere. Okay. So, this 5 ampere current is flowing towards node 3, that is why towards means plus 5 equals to 0. Okay. So, we already got y value 1. Here I am substituting y value 1 and minus z plus 5 equals to 0. So, what is your z value? 6. Is it right? Okay. So, Z means the current through this branch. Let us take resistance R. Current through R is 6 ampere current. Okay. So, like this you have to solve any network if you know two branches in at node except one branch current is unknown. By applying KCL you can find out current in that particular branch. Okay. Now, we will take one more example circuit and we will solve it. Now, here it is one more example circuit, and here how many nodes, number of nodes in this network. Now, let me take a spin mark. Now, see there are 3 nodes and these nodes are represented with letter A, B and C. Okay. So, in this the question is you need to find out current I6, okay, because I1 is given 2 ampere, I4 is given 1 ampere, I5 is given, sorry it is not 1, this is minus 1 and I5 is given minus 4 ampere. So, you have to find out I6 current means this one. So, what is I6 current? Clear? Okay. Now, see, now here I am applying because this I1 current is given how much? 2 ampere. This is 2 ampere current and I4 minus 1. Look at this, here I am taking minus 1. Okay. Now, I2 we do not know, so that is why these two currents are known. I4 at this point, let me take representation. Here I4 current and I2 currents, I4 and I2, I1 are known. That is why here I am applying KCL first at node A. Okay. Now, I4 is towards node plus I4 and this I1 is also towards node plus I1 and this I2 current is like this. This is your I2 current. Is it right? Means this is leaving node A. Means we have to write minus I2 equals to 0. Okay. Now, substitute the numbers. What is your I1? I1 is 2 ampere. Right. So, this is 2 ampere. What is I4? I4 is, this I4 is minus 1. Yes, I4 is minus 1. Sorry, it is, let me erase this. Now, here this is minus 1. Now, here I am finding the current I2. Okay. So, minus 1 plus 2 plus 1 and where I2 value will get 1 ampere. Okay. Now, here we got I2 value how much? 1 ampere. Okay. This is towards C. Now, can I apply KCL at node C? Yes or no? Because I5 is given how much? It is minus 4 and this current is 1 ampere. From here I can determine current I3. So, now here I am applying KCL at node C because 2 branch currents we know and the third branch current we need to determine. Is it right? Okay. Now, here I am applying KCL at node C. Clear? Now I2 is towards node, so that's why I am writing plus I2, and this I5 current is also towards node, that's why plus I5, and so this I3 current means like this, you have to extend this I3 current. It is leaving node C, means minus I3 equals to 0. Okay. Now tell me the value of I2, how much it is? I2 we got from this I2 1 ampere. Here I am writing 1 ampere. This is I2 plus I5. Do you know I5? Yes, I5 is given in the problem itself, minus 4. I am writing bracket in bracket minus 4. Now I need to find out I3. So let us take this I3 right side. Now minus I3 becomes plus I3. Is it right? Okay. Now 1 plus minus 4, it is 1 minus 4 equals to I3. What is your I3? It is minus 3 ampere. Okay. So your I3 is minus 3 ampere. Now here I am writing I3 we got minus 3 ampere. Okay. Now, so if this is minus 3 ampere, then what should be the value I6? For that I have to apply KCL at node B. Okay. Now here I am writing this equation with the green color. Now KCL at node C. Now look at this I1. I1 is like this. I1 is like this. What is I1? 2 ampere. So 2 ampere current is leaving the node. That's why minus 2. And I3 current is towards node. Okay, plus I3. So means I3 value we have to add. What is plus I3 value? Minus 3. Okay. Then I6 current is towards node. It is plus I6 equals to 0, 3 branch current. So the I3 magnitude itself minus 3, though that is plus I3, but I3 magnitude itself minus, plus of minus 3 is minus 3. Is it right? So now from this, what is your I6 value? I6 equals to minus 5 ampere. So like this you have to solve your network when Kirchhoff's current law by using basic Kirchhoff's current law at particular node. If 4 branches are there in the network, if you know 3 branch currents, by applying KCL the 4th branch current can be found. Okay. So now let us take one simple example with a different combination. Here I am giving one example problem, and this is for you practice problem. You practice this problem and find currents. So the first step is identify number of nodes. Okay. Then next apply KCL at node at particular node and determine unknown current. Here I am giving the nodes are A, unknown node A, this is the node A and this is the node B, and here it is node C. Is it right? So now at node A how many branches are connected? 1, 2, 3. Here the current is 1 ampere and here the current is 6 ampere. This current is I1 towards node. Okay. These two currents are known, but this is unknown. Apply KCL and find out that I1. Similarly at point B also, and this current is known current, this current is known current, leaving the node, and find I2 current. And similarly at node C, and this current is unknown current, it is I3, and this current is known current 7 ampere, and this current is 2 ampere leaving the node. Okay. So take the direction of current. If current is towards node, take positive, and if current is leaving the node, negative. Okay. So, like this you just practice this problem and find out the currents I1, I2 and I3. In next lecture we will see Kirchhoff's voltage law and problems. We already discussed the statement Kirchhoff's voltage law. What is that? Algebraic sum of voltages in closed circuit equals to 0. That we will see in next class, and thank you.